And we're back and better than ever. We're still in 10.1. And in the last podcast, we were showing you how to convert between moles and number of particles using Avogadro's number. In this particular podcast, we're going to take the next step and show you how to convert between moles and grams or mass. Now, the reason why this is so important is because everything that we do in the lab, or for the most part, we're going to be weighing things out on an electronic balance. And so, if you want to count the number of particles, you don't actually measure the number of moles, you measure the mass, and then you do the correct conversions. So how do you move back and forth between the mass in grams and the number of moles? Well, it actually is very simple. The periodic table tells you the molar masses of the individual element. In fact, if you take a look at, let's just say, gold. Gold has a molar mass. It's element number 79. Its symbol is Au. If you look on the table, it's going to tell you that the mass of gold is 196.97. Now, what does that mean? Well, that means that it could be the average mass in AMUs. That's something that we talked about back in Chapter 4. However, for our purposes right now, what it also tells you is the mass in grams of 1 mole of that substance. So 1 mole of gold is going to have a mass of 196.97 grams. Similarly, carbon, 1 mole of carbon is going to have a mass of 12.01 grams. Or if you want to pick, whatever your favorite element is, let's say that your favorite element is magnesium. I'm sure that's the favorite element of many of you. 1 mole of magnesium is going to have a mass equal to 24.31 grams. And so now you can use these ratios or these equivalent statements in fractions. For gold, you could put 1 mole of gold over 196.97 grams of gold. Or you could do the reciprocal. You could have 196.97 grams of gold on top and have 1 mole of gold on the bottom. And you could use that as a conversion just like you use Avogadro's number, or just like we use, say, the alien conversions that we practiced in class, if we actually did that this year. All right. So the power of the periodic table, part of that power is the fact that you can use the molar masses in conversions. Okay. And we're going to be doing that in the next section. Now, oftentimes we're not going to be dealing with individual elements. We're going to be dealing with compounds. So how do you do that? Well, let's start off with something simple such as water, H2O. If you have 1 mole of water, that's going to mean that you're going to have 2 moles of hydrogen. You have 2 hydrogens in every 1 H2O. So in 1 mole of H2O, you're going to have 2 moles of hydrogen. And you'll have 1 mole of oxygen. Scroll down a little bit here. So if you use the molar masses that are found on the periodic table to change from moles to grams, the molar mass of hydrogen right off the periodic table is 1.008 grams of hydrogen per 1 mole of hydrogen. Notice the moles on the bottom will divide out with the moles on top, and that gives you, that's an equal sign there, 2.016 grams of hydrogen in 1 mole of water. You're going to do the same thing with the oxygen. Oxygen is 16.00 grams per 1 mole, right off the periodic table. So the moles of oxygen divide out top and bottom. You're going to have 16 grams of oxygen in the water. So when you add that up, you have 18.02. I'm just rounding now. Instead of saying 18.016, I'm going to round it to 18.02 grams total in 1 mole of H2O. So we call the 18.02 grams per mole, that's how we generally write it, that is the molar mass of water. All right? Now, typically, we don't go through all of these conversions and calculations to get the molar mass. Typically, this is all we do. If we give you something like carbon dioxide, CO2, rather than writing out all of these conversions, we simply say that the molar mass of carbon is 12.01 grams per mole. The oxygen is 16 grams per mole, but you have two of those in the compound. And if you add those up, 12.01 plus 2 times the 16, you get 44.01 grams per mole as the molar mass of carbon dioxide. This is the way we typically solve it. But the reason why you can do it that way is because all of the units will in fact cancel out. All right? Let's go ahead and try another one. Let's step this up just a little bit. Let's go with, say, glucose, which is C6H12O6. What is the molar mass of glucose? If you want to pause it and give it a try, and then come back in, then we'll give you the answer. Okay, so here we go. We have 6 carbons, so you're going to have 6 times 12.01 grams per mole. That's the carbon. You have 12 hydrogens, so you have 12 times 1.008. You have 6 oxygens at 16.00 apiece. And when I take, with handy dandy calculator, you need it every day, 6 times 12.01 plus 12 times 1.008 plus 6 times 16, I'm getting 180.16 grams per mole as the molar mass of glucose. All right. Let's try just one more, and then we'll make this a little bit harder yet and see if we can't figure this one out. Let's go with copper 2 phosphate, which is going to look like this: Cu3PO4 in parentheses 2. If you want to give this a pause, then we can go ahead and give it a try, and then we'll get back together. All right, we're back. Now, with this one, you have 3 coppers. Copper weighs 63.55 grams per mole. You have 3 of those. The next element is phosphorus. Now, it looks like that there's only 1, but this 2 is on the outside of the parentheses, which means you really have 2 sets of PO4s. So that means you have 2 phosphorus, and each phosphorus is 30.97 grams per mole. And you have 2 times 4 gives you 8 oxygens at 16 apiece. And so when you take your 3 times 63.55 plus 2 times the phosphorus, which is 39.97, plus the 8 oxygens, I'm getting 380.59 grams per mole as being the molar mass of copper 2 phosphate. All right, that's important. You will have to calculate molar masses of these compounds throughout the trimester. So make sure you do practice that up, help one another out, practice it, ask questions, and we'll see you in the next podcast on 10.2.